Today is set aside for integer programming solution algorithms. Integer programming solution algorithms. But there is a surprise here. That as opposed to linear programming, which has the simplex method, and network programming, which has the network simplex and sensitivity analysis, which has well-established results, the integer programming solution algorithm is far from having been finalized. It's constantly being upgraded and updated with all kinds of methods, new methods coming out all the time. If I were to list the methods that we use, there's would be a large number of them, and I could sound very erudite by having all kinds of names up here. But if for me to start explaining what these methods are, I think goes well beyond the course. And even with even if we do spend the time, you would still not be able to solve any integer programming problem by hand. That is a task that is fairly impossible. It's conceivable that you can solve a decent size linear programming or network programming by hand with enough time, not weeks or months, but a couple of days. But you could not do that for integer programming problems. Computers sometimes cannot solve. Current algorithms aren't available to solve any arbitrary integer programming problem. As a matter of fact, there is a compendium of integer programming instances that haven't been solved and that people are still trying to find the optimum solution to. So I think it's best to view this day as another day to formulate integer programming problems. You had one day last week, and we've done a lot of things since. And I think we're going to take a little break, or it's near the end of the course actually. Tomorrow is the decision analysis, which is a totally different topic. So you're going to be given time today to solve more integer, to formulate more integer programming problems. But there are two methods that I will present so that you have some basic and some idea, and they are branch and bound. And it will not take very long to deal with this topic. Branch and bound, and the other one is cutting planes. And so I'll just explain what these are with a very simple example. What we're going to do is the branch and bound, we're going to apply the branch and bound methods to the same example that we've been doing over and over again with the tables and chairs. So the first thing that is done is that you solve the problem as a linear program, and if you're lucky, you get all integer solutions, and that's the end, but most of the time you're not. So let's say you solve it as an integer program, and you get this. So you solve relaxing what they're calling relaxing the integer constraints, integer requirement, and that leads to this solution here. So you get that x1 is equal to 2.5, x2 is equal to 4.5, and the objective is 11.5. We now know that we need to do some more work. We also know something else. We know that the absolute maximum that we can reach is 11.5, because as soon as we start putting more restrictions, saying that x1 and x2 cannot be a non-integer, then we will be reducing the objective. So the next thing that is done is you branch. Now, so you have to branch. So the question is, branching means that you take a variable like x1 and you say that x1 has to be either less than 2 or it has to be greater than 3. Similarly, if we branch, that's if we branch on x1. If we branch on x2, then we would say we would add two constraints. One saying that x2 has to either be less than 4 or x2 has to be greater than 5. And then we take it from there. So if you have a problem with 100,000 variables, it's a non-trivial matter to decide which one you should branch on. And that's where a lot of the integer programming problems, the actual solution methods, deal with questions like that. And we're not going to deal with that here. So let's say that we pick the first one. So we're going to branch on x1. So we're going to have to add two constraints. So we are here, and we notice that we take either x1 is less than or equal to 2, or we take x1 is greater than 3, and then we again solve the linear program with that additional constraint. And what we get is we get x1 is equal to 2, x2 is equal, still not integer, 4.66, and the objective is now 11.3. So the objective has come down as we expected, but we don't have an integer solution here. On this side, we're fortunate, and we have here an integer solution. And what that means is we call this an incumbent. We have an incumbent. We might run out of space here, so let's shift them over. Incumbent means that we have a solution. We don't know if it's in theory, we don't know if it's the optimal solution. For this particular case, you can pretty well tell it's the optimum solution, but there might still be a surprise. So we have an incumbent, and then we fathom what we say. We fathom this branch. We don't go any further because we already have an integer solution, so there's no more branching to be done. This particular branch, x1 less than or equal to 2, it still has to, we have to branch further. So this time we have to branch that x2 is either less than or equal to 4, or greater or equal to 5. So let's do that. The next slide. And what we have here is that we have an incumbent at 11. We have this branches fathomed, as we said before. And now we have two integer solutions. We definitely are going to fathom at this point, because there's no point going any further. And the same thing here. So what we've observed is that we have another incumbent. So we have one incumbent, and then we have another incumbent. And in fact, we now have two incumbents with exactly the same objectives, that equals to 11. So we have a choice. We can either have x1 equals 3 and x2 equals 4, or x1 equals 5, x1 equals 1, and x2 equals 5. So we have two incumbents, and they both give me the same objective, and that solves the problem to this point. This is the general method of branch and bound. It is a very elementary technique, but it is the core of most industrial strength integer programming methods. The next method that we will talk about is cutting planes.